All right, let's go with it here. So still in chapter 2, 2.4. This is going to be a little bit abstract of a section. Talks about just the whole concept of a function. And so we're going to hopefully get through this section here pretty quickly. Again, talking about domain and range, something you guys probably have seen before. Hopefully it'll clarify a few thoughts here. How do we identify a graph to be a function or not? Something you probably have seen before as well. And getting information about a function, and then eventually giving some application questions using functions here. So let's go for it here. Again, some quick definitions here. Hopefully probably looking at your textbook to get them as well here. Special relationship exists. Let's say y is equal to 10 times x. And really getting to the whole concept of function. Function is when you plug in one number, you get out a number as well. Good there? I think you've done that since Algebra 1. Remember that? X is called the independent variable. Y is called the dependent variable. And x is the one that we get to plug in. Y is determined based upon x only. So what in the world is a proper definition of a function? It's this little thing right here. It says the set x is the domain of the function. And as long as the rule says if I plug in a single x, I get out a single y, I'm good. If I plug in a single number called x and I get 2 or 3 or 4 different y's, I'm not good. I used to tell the little explanation of it. I think as Math 15 students, you guys should know already that whole definition here. But if you're a detective and you're trying to solve something, and eyewitness says, where were you at 3 o'clock? And the guy says, I was at home. Later on, you give the question again in slightly different terms. Whereabouts were you at 3 o'clock? I was at work. We got ourselves a problem, right? Someone's lying. So same thing with the function. If you plug in a number called x, you better get out a single number called y. All right, how do we look at functions? We look at them like this. This is called a mapping of a function, sometimes called a correspondence document or diagram. So if you say A is going to go to 1, B is going to go to 3, C also goes to 3, D also goes to a 4. This is perfect. That's a good example of a function. One element here only has exactly one element here. Where's the problem with this one? C is the problem right there. C is at home one time and they were at work the same time. Not going to happen, right? C is the problem. It goes to 2 different y values and no longer a function. All right, next one we got to sort of think about. Notation. We should think about notation here. So the middle paragraph is the one that's important here. So the number y, sometimes denoted as f of x. And what f of x means, that now you're talking about a function. If you just say y is equal to 3x plus 5, you're just talking about a simple graph. Could be a function, could not be a function. Once you put in a f of x or f at x, that little designation now says that it is a function. It has certain characteristics that as you plug in one value for x, you only get one value for y. Okay, so let's go with it here. Practice problem number 1. There's a A and a B. What I did is I included a letter C into the practice problems here. So I highlighted it, so made it red, just to show that's something extra I put in. And so we're going to take a look at how do you figure out whether something is a function 2 different ways here. So first of all, let's look at it just in terms of individual points. And again, this is straight off the practice problems here, except for C is an extra little piece here. So for A, 2 goes to 1, negative 2 goes to 1, and 3 goes to 2. Function or not a function? It's a function, because whenever you plug in a certain x, that x has only one corresponding y value. Good there? So are we okay with A being a function? B, 2 goes to 5, 3 goes to negative 2, 3 goes to 5. What's the problem there? X equals 3 is the problem. No, that is not a function, because 3 can go to a negative 2 and then also 3 go to a 5. I don't think so. And of course, my little interesting question here is C a function or not a function? What do you guys say? Let's do raise of hands. This will be kind of fun. Those in Fireball, real quick here, how many say yes, it is a function? Let's do that. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Those in Kalinga, how many say yes, this is a function? Okay, but here it's about 90%, there is about 80%. We good? 2 goes to 1, negative 2 goes to 1, but 3 goes to 2. Aren't these 2 points still the same exact point? So in this case, they still map to the same exact point on the graph. So yeah, that is still a function. They have to map to 2 different y values, 2 distinct y values. Okay, good there. All right, let's jump to a graph then. Again, probably don't write it down, but kind of think with me here. Which one's a function, which one's not a function? We'll go with it like that. All right, first one, what do you guys say, yes or no? The other one. No, good, all right. That's a no. At negative 1, here's our problem, right? So notice negative 1 goes to 2 and negative 1 goes to negative 3, and that's our problem. Hey, remember something called the vertical line test? If you were to put a vertical line across here like this, it'll hit at 2 different spots. So there's something called the vertical line test from algebra, right? Remember algebra? If you hit the graph at more than 1 point anytime during the domain, that means you don't have a function. So the second graph, yes or no? Yes. Yeah, it hits at negative 2, 1. Again, it only hits at 1 spot at most. So that would be a yes. Okay, so let's see. We looked at individual points. We looked at a graph. And now let's jump to looking at an equation. How can you tell whether a function or whether an equation is a function? That's what we're going to get into next. All right, and yes, you could pretty much tell just looking at it. And there's one specific thing I want to mention here. It says determine whether y is a function of x. And that's you got to make sure which variables are you talking about, because I can switch as well here, switch it on you here. So we're going to determine whether y is the function with x being the variable. So how do we do it? We start solving for y. And if you can solve for y, and you feel pretty confident that whenever you plug in one single value for x, you only get one single value for y, you're doing good. So in this case, if we start solving, we're going to subtract 2x squared from both sides. Don't really like the negative there, so how about this? How about we divide through by -1 or multiply through by -1, and that way we get and one more little step we got to do to solve for y. Take a square root of both sides. You know, the only thing is, usually we don't write it like this. We usually write the one in front, positive one in front, or one with the variable in front. Again, those two are the same thing. Usually in math textbooks, you'll have it written like this. But one more thing to do, take a square root of both sides, and don't forget, remember, if you're the one taking the square root, you got to put that plus or minus there. Unless you have been restricted by the domain, or unless it's a word problem, unless you're solving for distance like we did last time, then that's when you really know that it's a positive answer, a negative answer. Anyways, real quick here, so you guys tell me, are you fairly confident if you plug in a single value for x, you'll always get a single value for y. Yep, should shake your head no, because if I were to plug in some kind of number here, let's say 1. 1 squared is 1 times 2 is 2. 2 minus 1 is a 1, and square root of 1 is a 1, but then you're going to get a positive number. You also get a negative number, so you're going to get 2 values. In fact, it's okay up until you get to 1/2 at that point, or the square root of 2. Once you get to square root of 2, then you're in trouble, because then you're going to get all sorts of weird answers. Okay, so here it is. The answer is no for this guy. For B, again, solving for y. Whoa. Alright, subtract x from both sides. Get a negative 2y is equal to negative x plus 5. Divide through by a negative 2. Y is equal to 1/2 x plus or minus 5/2. So question to you guys, are you fairly confident that whenever you plug in a value for x, you're only going to get one single value for y? Yeah, I think so. Whenever you plug in stuff, there's no way you get a plus or minus of the answer. That's why. So just real quick looking back, this is the algebraic way of solving it. But you can really look at just the initial problems themselves. A, because of the little y squared, obviously, yes, that's what's going to be the problem, right? Because whenever you take the squared, you're going to get that positive negative. So whenever you have y squareds inside a problem, you know that's not going to be a function. You know, if it's linear, everything's linear, you know that's obviously going to be a function. Okay, so let's see. We looked at pairs, we looked at a graph, we looked at equations, trying to determine whether they're functions or not. Okay, let's go back just a little bit in algebra just to make sure we got it. Let's evaluate functions, something you guys should know already. And then C is a little bit of a twist there. All right. First things first, I want to point out a little bit something here. So this function right here, let g be the function defined by this equation. So since there's a y over here, we're technically not saying this is a function. When you say this is a function is when, I should have actually had arrows here. Let me put a little arrow like this. We're going to write it as g of x is equal to, okay, we're good there. Now I'm declaring that to be a function. It's a function g of x. But these are pretty easy ones here. All we do is plug in a 0. So this means g when x is 0. So plug it in and all done when we get a 0 out of it. That means this graph goes through the origin. All yours. Plug in a -1, see what you guys get. And of course the fun one, g of x plus h. And I think that's something we did in the first chapter we covered. It's something close to that. Alright, plug it in a -1. Hopefully this is what you guys got here. We're going to square the -1. That will turn it to be a positive, but you're still multiplying by a -2. So you got a -2, and then 5 multiplied by a -1 is a -5 eventually. And how about a -7 at the end? We good there? Alright, and if you got that, the fun one. Can you plug in x plus h? All right, this is the fun one here. So x plus h squared plus 5 times x plus h. And this you have to FOIL out. So off to the side of a sheet of paper if you need to. X plus h times another x plus h. I think we've done this 6 times this semester already, I believe. Maybe. Multiplying x plus h out. Again, off to the side if you need to here, but it should turn out to be x squared plus 2xh plus h squared because the middle doubles. It is a perfect squared trinomial. And you can distribute the 5 into there. Whew, the fun part is you got to distribute the negative 2. So negative 2 times x squared. Negative 2 times a positive 2xy xh. So distributing all that together. Alright, so with functions, yes, we can plug in whatever number we like. With functions, we can actually even plug in different variables. Sometimes in mathematics, we call it a dummy variable. So it's g of x, which means I could plug in whatever I want. I could put a triangle in there if I like. I could put a star in there, whatever you want to put in there. This is going to be common, x plus h. You'll see that this is going to be a little bit of a basis for calculus when we plug in x plus h. It's part of an equation that we use in calculus. Okay, so we got the whole function thing taken care of. We got plugging in taken care of. Let's just go back real quick here, review domain. I think we did that before. And unless you have ourselves a word problem that we're working on, and the domain is completely restricted because of the word problem, like you can't have negative wheelchairs, right? That'll automatically restrict it. Or it's a geometry problem where you're looking at distance, and distance has to be non-negative. If not, then what we do is we just take the largest set of real numbers that could be possible outputs. Okay, anybody tell me, what are the 2 times that we have domain problems with equations? Cool, okay, we got some fraction problems, right? Can't have a 0 in our denominator, so something looks like this. F of x is equal to 1 over x plus 5. We say, you know what, this is what we're going to solve. So x plus 5 can't be equal to 0. And here's the way we write it. We write it in terms of intervals. Good there? So what is the domain for that particular problem? It's from negative infinity to negative 5. And what we do is we put a little parenthesis, means I don't want the negative 5 here. Okay, union, and again, anything above negative 5 works as well. Alright, fractions are a problem. Any other problems with domain?
A negative under the square root or inside square root?
Okay, I'll go with that. Square roots or even roots. There's our problems. So something looks like this. G of x is equal to square root of x plus 5. This is not an individual point. This is actually an interval problem now, because you can't have negatives inside there. So what we do, that's the inequality we need to solve. X plus 5 can only be greater than 0 or equal to 0. And as we solve that, subtract 5 from both sides. And there's that. And can you guys convert that into a interval notation? Alright, let's see, x is greater than or equal to negative 5. That means we have a bracket on our hands, is that right? Bracket starting at negative 5, going off to positive infinity with a parenthesis. There's your interval notation. And again, I know you guys did this in algebra. You probably did something like this in algebra. Maybe a second fraction over here, like 1 over x plus 5 plus 1 over x minus 3 or something. I think you've done those. We're going to get a little more difficult here. What happens if we have situations like this. So let's sort of throw in a few little interesting problems into here. All right, so let's put it together here. So the first one, notice, let's see, we do have a square root and we also have a fraction, so both of them at the same time. So since the square root is in our denominator, the square root says that these numbers either have to be 0 or positive. Because it's on our denominator, it can't be 0. So it's a pretty easy solution. All that means is this right here, doesn't it? That means all the numbers just have to be positive numbers. So we drop the little equal to part because it's inside our denominator. So subtract 1 from both sides, and then remember when we divide or multiply through by a negative on an inequality, we change our, or we switch our inequality. Cool. That's pretty awesome. So we know at least what numbers will work over here. So any numbers that are less than 1 would work nicely in here. Anything that's equal to 1 or greater will not work for our domain. And the only other thing is, can you convert this into interval notation? Because this is the way we like to see them. We like to see them as an interval. So I got negative infinity to 1 and then also a parenthesis. Parenthesis means I'm not including the 1. If there's a bracket, the bracket means I am including that number there. What's some other stuff here? Infinity symbols always have a parenthesis next to them because you can't really get to the smallest number and you can't really get to the biggest number. So you always have a parenthesis there. Okay, B is the fun one here. I got a square root now. I got a fraction inside there. Oof. So let's see what we got here. First and foremost, I got myself a fraction. So let's talk about this here. So bx minus 3. I got this situation, is that right? The denominator of my fraction can be equal to 0, therefore x can be equal to 3. At least solve that one. Now we deal with the square root issue. So that the second problem is this right here. So notice what we're dealing with these separately now. Last problem we dealt with them together as one little piece. All right, because of the square root symbol, we call it the radicand. The stuff inside the radical has to be greater than or equal to 0. All right, you guys remember solving this in chapter, I think it was P.6 or something like that. We did something like that. So what we do here is we set them equal to 0 as opposed to with the inequality. There's also another thing we got to do. Remember something called the domain restriction before we start applying, right? We'll say x can't multiply by 0 on both sides of an equation. So you restrict the domain to say x can't be equal to 3. Therefore it allows you to multiply by x minus 3. Cancel, cancel. So x plus 2 is equal to 0. Subtract 2 from both sides, and we got this. But what does this give you? Gives you the place where it's equal to 0, right? This is the time where it equals 0. And so what we do is we set up this whole entire thing here. First of all, at 3, it cannot equal to 0. It's not part of our domain. So we put an open dot. At negative 2, we put a closed dot, which means it's hitting that 0. And we have ourselves 3 intervals here to deal with. Anything that's less than negative 2, in between negative 2 and 3, and anything that's greater than 3. So you guys tell me When is it true? When is it false? I'll let you guys do that as I look up a little something real quick. So you got to test each one of those intervals here. Let's see what we saw. No, we saw this problem in, let's see, in 1.5. That's right, 1.5 we saw inequalities, rational inequalities. All right, interval that's less than -2. This guy, true or false? Okay, pick -5 as my test point, and I got myself a true statement. That's what I did. So -5 plugged into here gives me a -3 over -8, and that becomes +3 over +8, and that is a true statement. That is bigger than 0. Okay, let's kind of think about this here just for a little bit. What we're really saying is, if you're at the positive values right here, if this is a graph and you're above the x-axis, the only way you can go underneath the x-axis is to either touch it or to have a break in the graph. We good? That's kind of what we're testing. We're testing, where's this graph? Is it above the x-axis or below the x-axis? Okay, easiest number to test between -2 and 3. 0 is good. Plug 0 in. 0 here, 0 here. That's going to be 2 over -3. True or false? That's false. All right, and then something bigger than 3. I plugged in a 10. 10's pretty easy. 100's even easier because you don't really care what the number is as long as you know if it's positive or negative at this point. Plug 10 over here. That's going to be 12 over 7. So 12/7 is going to be greater than or equal to 0. That is a true statement as well. All right, let's see what we got here. First of all, are we including the time that it's equal to 0? Yes. Remember this inequality here? So we are including this -2 in our answer. And so what we want to do is we want to graph this area here and then also graph this area here from 3. So -2 going down and from a little bit above 3 going up. That's my answer here. You guys get to turn it into interval notation. All yours. So I got -infinity to -2 with a bracket. Union 3 is not part of our domain at all, so it's going to be a parenthesis and then off to infinity. Whew, that was a long one. A was pretty easy. B was a little bit more intense there, so we're going to have a good range of homework questions on that one. Okay, the next set of stuff we got to look at is just a whole bunch of questions based upon graphs. Just so can you sort of answer questions based upon what you are given. And this time we'll deal with range. Later on we'll deal with just a whole bunch of questions there in that way. Alright, so let f of x equal to x squared. And what I did is I restricted the domain. I restricted it from -3 to +3. first thing you should know is you should at least have a sense of what x squared looks like as a graph. We'll figure out different ways to find the range of equations here when we get to exponential equations and functions and logarithmic functions here. But for now, x squared, you guys should know you should have a graph of x squared. So let's see. If I were to plug in a -3 into x squared, it gives me a 9, is that right? If I plug in a +3 into x squared, that also gives me a 9. And then you should sort of know the graph of x squared. So tell me if you guys agree here. A is a no. Is that right? And y, let me answer B, because A and B are roughly the same question here. Because if I take a graph of x squared, and my endpoint over here is a graph here. There's my -3, 9 right here. I know it goes through 0, 0, because that's x squared. And then we got a +3, 9. So this graph does this, doesn't it? This is x squared restricted from -3 to +3. So for range questions, you do need to see a graph somehow, or at least you should think about what the graph looks like. So is 10 in this range? No, because the highest this graph goes is just a 9. So is 4 in the range? And yeah, if you talk about range here, what you're really saying is right here at y = 4, can I get to a graph going sideways? Yeah, I actually get to 2 of them, that's fine. So 4, yes, that is inside this range. If you think about range, you should probably almost like highlight from 0 to 9. In fact, let me do that. Let me highlight. Highlight should be here. Again, that's my range for this particular function. How do I say it? I say it like this. The lowest point is 0, and I am including 0, so that means it's going to be a bracket. And the highest point is 9. And do we include 9? Yeah, it's part of the answers we get. So there it is. There's my range is the y values that have a corresponding graph to them if moved horizontally away from the x-axis. Okay, we're good there? So we got domain, we got range. We'll deal with them quite a bit, because in calculus, based upon the domain of a function, you will be able to take something called derivatives or take integrals of things. That's kind of what we're getting to. So range is the y values. You pretty much, again, need to see a graph of it to get that. Okay, so we talked about it already before, but something called the vertical line test. Oh, before we even get there, there's another way that math textbooks write range. This is called set notation, and the reason why it's like this is because it includes that little y value in there. Because then at that point you know exactly what you're talking about. You're talking about the range, and it says the range goes from 0 to 9. This is called set notation. So the way you write it is you say it's the set of all y values. This little bar line means such that 0 is less than or equal to y, and y is less than or equal to 9. Cool. That sort of makes sense there. Okay, let's go. Next one, we already talked about it here, something called the vertical line test. So we'll do this one real quickly here. We already talked about it here. So again, if no vertical line intersects the graph of a relation at more than one point, then the graph is a function. So you could cross at 0, that's fine. Cross at one single point, that's fine, but you can't do 2 because then you no longer have a function. So again, this guy would not be a function, 2 different spots. And notice that the a value corresponds to b. A value also goes to another point called c. There's a problem. Okay, don't need to write them down, don't need to graph them, don't need to draw them. Just kind of let's work together real quickly here on them. So just say yes or no to see if this guy is a function or not. see most people saying no. Yeah, not a function. Right there is the problem, right? You got two corresponding points that if you put a vertical line over here, they will touch at the same time. That's a no. Yes or no? No way. Again, it crosses at 3 different points. The x-axis actually touches at 3 different points. Notice also if I put the vertical line here, it's only going to cross at once. So it's really just finding that spot where it does not fulfill the vertical line test. So yes or no? Yes. I go with the yes on this one, yeah. If you put a vertical line, it's only going to cross once all the way through. And yes or no?
Yes.
Again, this one's a yes. You can kind of go through it here. The reason why functions are very important is because when we deal with time, a lot of times we deal with time. And so you can't have a height of a missile at 2,000 feet at the same time 4,000 feet. That's not going to compute very well, right? Especially when you want to shoot down a target somewhere. And so yeah, it has to be only one single value for every single input. Okay, that's a yes. And this one, this is the practice problem itself for number 7 here, and I heard a no already. It's those points there, right? Not going to make it for the vertical line test. Okay, the next part of this section is just being able to answer questions based upon a graph or based upon an equation here. So again, practice problem number 7 should be a no. But let me give you this here. Let me give you a function, and then you need to tell me a few things about the graph. But what you're going to try to do is not graph it. You're going to try to figure it out algebraically. So really these are geometric or geometry questions, but I want you to solve them algebraically. Okay, just try it yourself first here. So I got f of x is x squared plus 4x minus 5, and the question to you is 2, 7 on the graph. And again, you want to answer that question without graphing it. So somehow figure out an algebra method for answering a geometry question. Alright, those who want to work with me on this one, let's go for it here. Those of you that can stay ahead of me, go for it. So, is the point 2, 7 on the graph of f of f? Well, all we got to do, we're going to plug in the 2 for the x and the 7 for the f of x. And if we do that, all we need to do algebraically is to figure out if that is a solution. Right? Because geometry, really, those graphs are really solutions. Alright, let's see, that's going to be a 4, that's going to be an 8, that's going to be 12, and 12 subtract 5, hey, that is a 7, cool. So the answer is yes, that point is on the graph, which I think is actually fascinating. We're actually solving geometry problems using algebra. That's kind of cool. Okay, next question. Find all the values of x such that x comma negative 8 is on that graph. So think about this one. Let you guys have a little bit of time thinking it through first. All right, those who wanting to do it with me here. So B, let's see, I'm trying to figure out when x comma negative 8 is a solution. So what I do is I plug in a negative 8 for my y value, leave my x alone, and I'm going to solve. Let's see. Oh, I see an x squared. And that's x squared, and I'm trying to solve this, so therefore I'm going to move everything over to set equal to 0 and factor once I see that x squared. So how about add 8 to both sides? Got myself a positive 3. Factor it down, 2 numbers multiply to 3, add to 4. Everybody's shy, don't want an answer. 1 and 3, we'll go with that, or 3 and 1, either or is fine, yep. And again, solving each of those, set equal to 0, or you can just give me the answer right away, that's fine too. So I got x is equal to negative 3 and negative 1. Then again, I want to give you the flavor of what the book does, and then also what other textbooks do, so you kind of see here. So your book, the way it'll answer it is like this. It'll answer it as set notation. It's going to say, oh, negative 3 and negative 1. There are 2 answers that will look like that. Other math textbooks, what they do, they write it out like this, and that's fine too. All 3 really are correct answers, and all 3 are accepted on the test, of course, because they're all the same. Okay, but we should realize this. What did we just come up with? We came up with the fact that if y value is a negative 8, I know 2 points that are also on the graph. Negative 1, negative 8, and negative 3, negative 8. We good? That's sort of what we realized. All right, C value. And again, we're just answering questions here based upon C. Find the y-intercept of the graph. Again, we talked about intercepts already before. So when do you have a y-intercept? You have a y-intercept when x is equal to 0. That's when you have a y-intercept. So really what you're doing is you're solving for this particular question right here. No. You're solving for 0 comma y at this point. Alright, now let's do that. You get yourself in negative 5, and that's good. Therefore, the y-intercept is negative 5. And then we also have another point that we can use. Now we know that 0 comma negative 5 is a solution to this graph. Alright, almost done with this one. It's a long one here. So find any x-intercepts. And so think about what you're going to try to find there. And again, all the x-intercepts, the thing that they have in common is that the y value is 0. So very similar to the previous slide. D, we're going to set the y equal to 0 this time and solve. So again, we're solving something that looks like this. When does that happen? I've got to factor this down then. 2 numbers multiplied to negative 5, add to 4. Cool. Positive 5 minus 1, we good? Set each of them equal to 0, of course, and solve. But you guys are sophisticated Math 15 students. You guys can do that in your head already. So I got these guys here. So y-intercept is a negative 5 and positive 1. What else do I know because of that? Let's see. I got 2 more points here. Negative 5 comma 0, 1 comma 0. Hey, okay, so this whole entire problem that we've done for A, B, C, and D, can you plot each of those points? And based upon those points, can you make your at least a rough graph of what we've been considering? Yeah, absolutely. So really the important points here, let me just draw it out. Again, the homework does not say you need to graph it afterwards, because the whole point is to understand that you've done algebra in order to answer geometry questions. That's what you've done. But here's my -5, 0. Here's my 1, 0. My y-intercept, which is 0, -5. And then when does it reach a y value of -8? It's all the way down here at -3 and -1. Based upon that, can you tell what the graph's going to look like? Yeah, it's rough, but not bad. Okay, what's the important points of a graph? Absolutely. X-intercepts, y-intercept. For parabolas, the only other point that's really important is the vertex. Because once you know the vertex and maybe like the y-intercept, you're done. You got yourself a graph. X-intercept's important. Again, if you're launching a rocket, you kind of want it to land at a certain spot, not just anywhere. That's my thinking. Okay, with that, again, not so much algebra, so much processing and thinking about stuff here. So let's put a few things together here. I'm going to arbitrarily put some graphs here. Based upon the graph itself now, can you give me the domain and range? Let you guys try it first. This is example number 9. I kind of thought that it's sort of needed before we get to the practice problem number 9. So can you guys do this thinking through? So domain is the x values, range is the y values. Give me domain and range for each graph, then we'll do the practice problem. So I'll give you guys a minute here. Try it yourself first. See if you can do it without any help. After you're done, if you're done early, take a look at your neighbor's paper. Then if you got the same thing, then you might both be wrong or you might both be right. We'll see. Changes. Okay. All right. Let's go for it, at least through A together here. So looking at just domain, that's what I want to look at. So there's nothing at -4 along the x-axis. There's nothing at -3. Once you get to -2, there's my start of my graph, right? So just looking across the x-axis, so starting at -2, and it looks like it goes all the way up to 3. That's when the graph stops and you're done. Few things we should notice: an open dot. Open dot means you're not part of the graph. We don't want to include that piece right there. So as far as domain goes, there it is. We're going to put a parenthesis at -2, and we're going to put a bracket at 3 because we want to include that 3 because that closed dot. So how do you write it? Interval notation, domain, and I usually just put a capital D for domain. You can put an equal sign or just colon, that's fine too. But I got -2 to 3 with a bracket. Good there. All right, let me switch the color here, and again, thinking about now the range. Range is right here, right? It's along the y-axis wherever you see a graph. So the lowest point this graph goes is a 1. Notice I'm just looking at y values now. Including 1 or no? The highest point it goes is a 4. Including the 4? Yes, sir, because of the closed dot. So there it is. So how about range? Capital R for range, and we got ourselves a negative, a parenthesis, 1 comma 4 bracket. Okay, good there. That was the easy one. Now let's take a look at something that maybe has a break in it. So B. So again, looking at the x-axis only, thinking about domain, where do I have a graph? I have a graph from -3 to +1. And then looks like starting at 3 again, I have a graph forever this way. Question real quick, including -3?
Yes.
Yeah, there's a closed dot, that's included. Including +1? I think so, because of the closed dot, and including 3 because of the closed dot. So I have a bracket -3 to 1. Then we got this little union again, union, and then again 3 to infinity. Good there? Okay, so now turning our attention to the y value here. So if you guys agree, is that right? Looks like the lowest point on this graph is -1, goes up to +1. And then here's a weird thing. If you go up here, there's no graph, but there's an individual point called 4. Good there? So here's what we do. We go like this. We say range is from -1 to +1, union, and then since we want just an individual point, what we do is we put in a set notation. Put these little braces, we call them. So the interval from -1 to 1, union, the individual point called 4. Alright, you guys get the next one here. This is practice problem number 9. All yours there. Can you give me domain and range? And again, tell me if I'm going too fast. I can slow down. Again, give you guys a minute or less than a minute here. Try yourself. Alright, again, looking at the x-axis right here only. I'm going to go from -3, and I'm going to go all the way up to, hey, hold on though, real quick here. Let's talk about this one here. -3. When you get up to +1, this is a closed dot, right? But that's an open dot. And then when you go just a little bit more than 1, you're on this line. So there's a little tricky trick here. There is no break for my domain. Very good? Because there's no space where, because if you say what's 0.9, 0.9 you're going to use this graph. What happens at 1, you're going to use this graph. What happens at 1.1, you're going to use this graph. So there's really no break in your domain. Cool there? Ha, gotcha. Okay. Range. This one straightforward like we did before here. The lowest point on my range is -2. There's an interval that goes all the way up to +2, not including -2, so parentheses. Because of the closed dot at +2, there's a bracket at 2, and then an individual point of 3. That one you should got from the previous example. Okay. Debating here. So I'm gonna skip a few little things here. Let's want to look at just a couple example problems here, or at least application questions here. How about this here? I'll let you guys do one problem out of here. I got like 4 set up, but let's just do one, then we'll jump to the next section here. So let's just look at this one. I will let you guys do the fiber optic cable problem here, but let's look at some other ones here. So cholesterol reducing drugs here. Many drugs used to lower high blood cholesterol levels. And something called bioavailability. The amount of drug you have ingested that makes it into your bloodstream. Again, that's huge, because if something doesn't make it into your bloodstream, it's really not happening at all here in your body here. So here's a graph of a certain kind of drug, and let me go back here. So a certain kind of drug, it has a 30% bioavailability. So Boris, according to the example, takes 20 milligrams per day. The question is, what's the maximum amount that he can have in his bloodstream? This is kind of interesting. Those of you guys going to the medical field, check this out. Check this graph out. Per day, if he just takes 12 milligrams per day, again, because of the bioavailability issue, he's going to take the first day. Let me go back real quick here. He takes 20 per day. It only has a 30% availability. So the first day that he takes it, he's only going to really, in his bloodstream, there's only 6 milligrams in his bloodstream. Takes it, and then half of it is filtered out the next day. So then really when he takes the next one, he's only about 3 now left right in there. So notice what happens here. Look at this chart here. It goes up to 9 now, because again, when he's down to 3 by the time he takes it the second day, then he boosts up to 6 again. Then half of that is gone out of his body, and then he boosts up again. So taking 20 milligrams per day, he approaches a maximum concentration of 12 milligrams in his bloodstream. I thought that was kind of interesting. The fact that it's different. You think you're actually taking 20 milligrams, you're not. It's actually it's thought through what you're going to have in your bloodstream at that concentration. Okay, so based upon this, real quickly here, again, I'm not going to let you guys do it here. Use a previous slide to figure out the range of the function. What's the range of this function? Assuming day 1, though, not assuming 0. What's the lowest point? 6. What's the highest point? Including 12, or no? Does he actually ever reach 12? Can he ever reach 12? No, not the way he's taking them. So we got a range of including the 6, but never reaching 12 per se. Painkiller drugs do the same thing. What they do is they go away from your body, but you want to maintain a certain level, and that's exactly what. That's why whenever you get your teeth pulled, the doctor says take these once a day for 20 days. So what's happening is the doctor is really making sure you're like right here concentration. You're about right here. You're around 12, 10, 12, so that the pain is not as severe. But that's kind of what you're doing with pain medication. Okay, and then also compute C of 11. Ooh, that's kind of fun. Again, think with me here for a little bit here. Based upon, there's 10, so we have to use this guy here. And then what we do is we have to take half of that, right? Because the previous day's concentration falls by half. And then we add another 6. So it'd be half of what day 10 was, plus 6 more. And again, just sort of seeing, you're getting pretty close to 12 though. You got 3 decimal place accuracy. So if all intents and purposes, you're at 12. But not computationally. Okay. See if I have time. Thinking I don't have time here. Let's kind of go through these just real quickly here. I'm going to skip this one here. I'm going to go to the practice problem here. I can't do that. Sorry. Change my mind here. I'm going to do example number 11 in your book. Those who are not going into the medical field, those who are going maybe into engineering field, I got this one for you. I got 2 points, A and B. Here's A over here. Here's B. They're opposite each other along a riverbed. And then there's a stretch of 1,200 feet from here to here, and eventually getting to point D. And here's our little problem. The cost per foot of cable is $5 per foot if you go under the water. If you're just putting in land, by the time you dig up the land and you put it in and you seal it back up again, it only costs you $3 per foot. So it's cheaper to go by land than by river. So now the question is, you want to get the most cost-effective path. What is that going to be? I thought this was kind of cool, so let's go for it here. So this one, 500 feet across. Notice it is going to be a right triangle. And this whole piece right here is going to be 1,200 feet from the distance if you go straight across. So if you went straight across this way, 500, then straight across this way, not a good idea, because you're losing a whole bunch of money in the process, because you're using too much cable up as well. So the question is, what is this point P that's actually going to minimize the amount that you need to use or cost? So anyways, that's kind of cool. So real quick here, if you think about it, this is a right triangle. Anybody give me a formula for the hypotenuse? Something called Pythagorean theorem, I think, right? Isn't this 500 squared? Is that right? Plus x squared, and then take the square root of that, right? So $5 here, $3 here, and Pythagorean theorem says this right here, and then I got to take the square root. That's the water. And so the distance in the water, or distance from point A to point P, looks like something like that. Is that right? Anyways, I'm going to finish up the problem here because I know there's a few things. I think you guys have 1 or 2 questions on the homework that deals with some word problems here. So, okay, there's the distance here. So how do you calculate cost? Well, here we go. The distance from A to P, that's that Pythagorean theorem that we talked about. The distance from P to D, that's going to be 1,200 subtract x, whatever x is going to be. And then the total cost would just be 5 times $5 per foot underneath the river, $3 per foot on land. The only problem is I can calculate cost, but I can't minimize it because I need calculus to do that. Oh, bummer. Almost at the end of the problem, but not quite. Isn't that sad? So we can set up the equation, we just can't solve it yet. We'll need a little bit of calculus for that. Okay, that's more like an engineering problem. I do want to show you then a business problem as well, which I thought was kind of fun. Some stuff associated with business. Whenever you talk about cost, if you cost something, there's something called a variable cost always. There's something called a fixed cost. Fixed cost is usually like a lease on a building. A variable cost is how much it makes to produce that item. So if we're talking about shoes, if you lease a warehouse for $100,000, if you make no shoes whatsoever, you're going to still be out $100,000. Good. And if it takes you $1 to make a shoe, then to produce one shoe, it's going to take you $1,001, right? To produce 2 shoes, it's going to take you $1,002. So there's your variable cost, is $1, but your storage fee is humongous. Okay, I think this one right here, the average cost, is really interesting. This is called how much does it take? Well, the average cost. How much does one thing cost? So go back to our example here. If we got a warehouse for $100,000 and we produced 1 shoe, what's the average cost per shoe? Well, let's see, $100,000 plus 1 makes $100,001. Divide by how many we made is 1. That's a very expensive shoe, is that right? I'm not willing to pay over $100,000 for a shoe, sorry. But how about if I can make 5? How about if I can make 1,000? So that's where average cost comes in. So real quickly, let's look at candy bars. If it fixed cost, I buy a warehouse space and it costs me $1,000 to lease it for the year. My variable cost, I can produce a candy bar for $1. and again, just kind of quick little thing here. So what's the average cost of producing one candy bar if I just produced one single candy bar in the whole year? Pretty expensive. And I don't know why I put that there. It should be $1,001. Nah, let me correct it here. So, everybody agree there? And I don't think anybody's going to pay over $1,000 for a candy bar. Even though the most expensive dessert, at least in the United States, is a hot fudge sundae served in New York with gold sprinkles, and it costs $1,500 per plate. So unless you really want to eat that and some metal with it. Okay, but let's look at average cost. How about if I can produce 10? Just 10. Give me 10. So it's going to be $10 plus 1,000, which is my fixed cost. But now I get to divide by 10. So anybody willing to pay $101 per candy bar? Still no. So then I got this problem. How about if I could produce 1,000 candy bars in a single year? What's my average cost per bar? Well, average cost is 1,000. Variable cost is 1,000 now. Fixed cost is 1,000, so it's 2,000 divided by 1,000. And if it's good, I think I might just pay $2 for a candy bar. Good? I think that's actually interesting, way interesting. If you guys remember 5 years ago, I think it was, GM got in trouble because what was happening is their average cost was more than, so to produce a car and to sell a car cost them, cost them more because they're still paying for pensions of people that retired, right? Workers' comp, insurance, all that good stuff they pay. And so when they got down to it, the number of cars they sold per month were still less than what they owe in obligations to pensions and retirements and workers and all that stuff. So they were about to go under really quick. And so that's all this average cost stuff. So this kind of cool deal here. Let me go to this one right here. So I got this little...
It looks like a prop from a sci-fi movie. Or possibly a ride.
Okay. So I got this little car over here that can fly. Small little problem. The engineer, brilliant guy. He's made patents for the U.S. Army, Navy. He's made millions of people. But he has invented a sky car called the Moeller Sky Car. And again, prototypes are done. The military actually had fun playing with them already. One small problem. His average cost is too high to introduce it into the American public, because in order for him to make one and sell one, it's roughly, I think it's like $500,000. So he has to be able to sell a whole bunch to get that average cost down, and then he can finally make a whole bunch of more money than he has already. Quick little interesting stuff here. President Bush, when he came into office, the second one, not the first one, one of the first things that he did as an executive order is to build a supercomputer. It cost $1 trillion, and it was a supercomputer in which it could instantaneously figure out and course correct 1 billion objects flying in the US airspace. And so even back then there was some talk about putting some flying cars out. That'd be kind of cool, wouldn't it? Just kind of hop on a car, fly somewhere, be done. CEO of American Airlines has already said that the last pilot has been born in the US. So he's looking at most likely this sort of taking over in at least your guys' lifetime. Maybe not mine. Okay, but again, the whole concept of average cost, I thought that was kind of cool. We'll see if it comes to fruition or not. We'll see. Okay. Okay. You know, I'm at a loss here. It's 6:30 already. I didn't watch my time too well here. So let's finish off this section here today here. So something called a linear price demand function. If you guys take economics, you guys will know that demand curves are not linear functions, they're actually quadratic functions. And they kind of come down like this. Ever seen this? You guys took high school economics or not? You got a demand curve and a supply curve like this. Ever seen that? And so we have something called the equilibrium point, which demand and supply equal each other. And that little guy always moves. And so if you're in retail, or if you rent apartments, or if you have real estate, you always want to figure out where that equilibrium point is at and hopefully hit that spot. Okay, so let's go for it. One more equation we've got to deal with here is revenue and profit. It's something you guys already know here. As well, let's finish off with this problem here then. All right, revenue is what are you charging to sell it and how many you sold, is that right? So it's price times quantity sold. Profit function, again, it's revenue subtract cost. So after you received your revenue, you subtract all your costs, and now you got yourself a profit. Quick story on that before we go on is got an acquaintance. He used to own 3 or 4 gyms in Fresno. Per gym, his equilibrium point, which means his cost per month, and his revenue per month, equilibrium point was $50,000 per gym, which means by the time he paid on the lease on the equipment, by the time he paid the lease on the place itself, paid employees, paid the workers' comp, paid insurance. So yeah, there were some times where he didn't make $50,000. But when he made $50,000, that just meant he made 0, right? And then anything he made above that, that's actually finally profit. So again, big risk. And then the best thing to do, just sell it when you're ahead. And that's what he did. Okay, anyway, so let's look at breaking even. And we'll finish off with this one. So today we'll just do one section. Slow down a little bit here. I'll adjust the calendar as we go. So Metro Entertainment Company spends $100,000 on production costs for its off-Broadway play. Once the play runs, each performance costs $1,000, and the revenue from each is $2,400. So here's what we got to do. We got to put in some functions here. Can you write for me the cost function for this play? Can you give me the revenue function? Can you give me the profit function? And then the most important thing is determine how many showings of Bride and Prejudice must be held for Metro to break even. Again, they couldn't use Pride and Prejudice, so they twisted it so they don't have to ask for a copyright. Alright, this is the example from the textbook here. We could actually even do the practice problem here, but we'll start with this one. So cost function, how much does it cost to do this? Well, let's see costs here. They spend $100,000, so this is their fixed cost. If they run no plays at all, they got themselves a problem and they are $100,000 in debt. Also, to run each and every show costs them $1,000. So tell me if you guys agree. 1,000 times X plus $100,000? That's A. B, write the revenue function. How much will they make per play? I heard it in a whisper again. 2,400 times X. And again, the profit function is just going to be the revenue, subtract any costs. Notice the cost has to go into a little parenthesis because you're subtracting 2 terms here. So as you distribute the negative into here, and eventually simplify. There's my profit function. We good? Now the question is, what do they need to do in order to break even? So you can kind of think of it two different ways. You can think of it, when does cost equal revenue? That's one way to think about breaking even. Another one is when profits are zero, right? You didn't gain anything, you didn't lose anything, now you're just at zero. So what we do, when profit is equal to zero, so we set that previous equation to zero, and we find out they have to get about 71 shows to break even. So now you guys think about tours, bands that go on tour and they're scheduled to perform every other day. That's exactly what they're thinking. They're thinking, okay, I need to do these many shows in order to break even, and then from here, now I got myself some profits. So think on that. Okay, so practice problem for you guys. Can you guys do this here from beginning to end? All yours. I'm going to change the numbers just a little bit here. So they still spend $100,000 for practice problem number 12. Each show now costs them $1,200 instead of $1,400, and the revenue is $2,500 instead of $2,400. Can you finish A, B, C, and D? All right, I'm going to give you answers to the first three. See if you guys agree here. Cool. Got a few people still copying it down. Go for it here. And if you got that one, try D by yourself here. When does profits equal to zero? Or when do revenue and cost equal each other? All right, and D should be shows. Let me spell it correctly here. Not shoes. Going a little too fast there. So I got 77 shows to break even. Then from there on out, maybe, sometimes. Okay. All right. Didn't expect 2.4 to take all class period here, so we are going to be a little bit behind. I'll take a look at the schedule here, see what we can do about that as well. All right, I think we're good to go. Any further questions, please come talk to me. I do have
What do you mean?
progress report to fill out as well here. But see you guys on